For our second part of section 1.3, we're going to be talking about rational exponents. Rational exponents are just another way of saying fractional exponents. So, we're going to start by introducing a couple of important facts. The first one saying that x to the 1 over n power is equal to the nth root of x. Meaning that whenever you have a fraction in your exponent, the denominator of the fraction is the same thing as the radical index. So you can convert from a radical to a rational exponent or a rational exponent to a radical as long as you keep in mind that the denominator is this value of your root, the radical index. So with that in mind, let's go ahead and try to simplify 8 to the 1/3 power. So we're going to use this conversion here that says 8 to the 1/3 power is equal to the denominator of this exponent 3 being the radical index. So 8 to the 1/3 is the same thing as saying the cube root of 8. And we know that 8 can be rewritten as 2 times 2 times 2, or 2 to the 3rd power. And like we discussed in our last video, the cube root of 2 to the 3rd, or whenever you have an odd radical index and the same power inside of it, they cancel each other off, leaving you with just what was inside. So 8 to the 1/3 power is just 2. Remember, if this were an even power, so if this were a 4th root and this were a 4th power, it would be the absolute value of 2. From here, we now have another fact that goes on the same topic but adds one little extra part to it. Notice this was x to the 1 over n power. Now we have some value a to the m over n power. So, whenever we have some value in the numerator, we have two options. The first is to say that a to the m over n is the same thing as the nth root of a to the m. And we could also say that it's the same thing as the nth root of a, all being raised to the mth power. Each of these has its own purpose. We use this first one if we cannot simplify the nth root of a. So for instance, if we were doing this last problem and we had 4 to the 1/3 power, we cannot simplify 4 to the 1/3 power. Notice we can simplify 8 to the 1/3 because 8 has a power of 3. But if we had a 4 here, we would end up with the cube root of 2 squared. So 4 would not allow us to simplify this. It doesn't give us a large enough exponent. So we wouldn't be able to use this case here. This one wouldn't help us. We can't simplify, we wouldn't be able to use this case, that is to say, because we wouldn't be able to simplify the cube root of 4. We would need this case. We would first have to evaluate the numerator of our exponent, and then we could start simplifying the root. Okay, so this case is the most common one that comes up though. Typically you are going to be able to simplify. You are going to be able to do something like this where you can change 8 to 2 to the 3rd power and then break it down before you apply the numerator of your exponent. Okay, so let's go ahead and try these in some examples to make more sense of that. We have 10,000 to the 2/4 power. the first thing we're going to do is to decide which of these two cases we want to use here, because we have an exponent that does not have a 1 in the numerator. So it's either going to be 10,000 to the second power and then a fourth root all on the outside, or it's going to be the fourth root of 10,000 all being raised to the second power. And remember, we decide this based on whether or not we can simplify that root with just the 10,000 in it. So let's go ahead and try this case first. Like I said, it's the most common one because it should typically be the first one that you go to. So we take our denominator, 4. We have the fourth root of 10,000. And that's all being raised to the numerator. We are squaring it. So can we rewrite 10,000 to some power of 4? Can we rewrite it as a base with some power of 4? Because if we can, then we can cancel this out. And if we take a look at 10,000, there's a trick whenever you're working with some number that's either 10, 100, 1,000, 10,000, 100,000, a million, and so on, anything like that. You just count the number of zeros you have. You take 10 and raise it to that power. So 10,000, we'd have 1, 2, 3, 4 zeros. So that's 10 to the 4th power. And now notice this is going to simplify. The fourth root of 10 to the 4 is the absolute value of 10, all squared, which leaves us with 100. Always remember that trick. Whenever you're dealing with a 1 with a bunch of zeros after it, just count the number of zeros, and that converts to the exponent. Okay, now one more important thing to note is, yes, for those of you that noticed in the beginning, you could have simplified this exponent to 1 over 2, but this problem was purely to demonstrate a more basic example of these types of problems. It would have been a lot simpler to just change this to 1/2 in the beginning, but it was just to demonstrate this fact. So, from there, let's go ahead and try another example. At this point, I'd like you to take a moment to pause the video, go ahead and try this on your own, and then we'll come together and try it. Okay, so from here, the first thing that you should check is, can we simplify this if we put a cube root over this negative 125? And because this is such a large number, there's a pretty decent chance that we will be able to. So let's go ahead and give that a try. We want to find the cube root of negative 125 all to the second power. Negative 125, notice it ends in a 5. If your number ends in a 0 or 5, then you can divide it by 5. So, let's see what happens if we were to divide this by 5. I'm going to do the prime factorization over to the left. If we divide by 5, we'll be left with 25. And 25 is just 5 times 5. We have all of our prime factors circled, so we know not to continue from there. So we end up getting the cube root of negative 5 times 5 times 5. And remember the trick that we talked about in the last video. For every pair of positive factors, you can change them to a pair of negative factors that are being multiplied, and it will not change the problem, because two positives multiplied together have the same result as two negatives multiplied together. So we get the cube root of -5 times -5 times -5. We started with that negative, we introduced two more negatives. And now notice we can rewrite this as the cube root of -5 cubed, all to the second power. And now we can apply our rule. Cube root and cube will cancel out, leaving us with just that -5 to the second power, which gives us 25. So -125 to the 2/3 power is just another way of saying 25. So from here, we're going to introduce another fact and process. The first fact that we should introduce is that all previous exponent rules, so all the previous exponent rules we introduced in the last video, still apply to these rational exponents. If you're multiplying with the same base, you can add the exponents, even if you have two fractions as the exponents. If you raise an exponent to another exponent, again, even if they're fractions, it will still apply. You can still multiply them together when you raise one to another. So with that, we say that to simplify radicals, another way that we can go about it, rather than just writing out all the factors like we did in the last video and canceling out however many we have depending on the radical index, a faster way to approach it is we are now going to be able to convert to rational exponents. Once we do that, we will simplify the fractions and then convert back to radicals. If you start with a radical, you should end with a radical. If you start with a rational exponent or fractional exponent, you should finish with a fractional exponent. Your problem should always end in terms of what it started with. So again, convert to rational, simplify, convert back to radical. Let's go ahead and try this out. We have the fourth root of the cube root of x. So for this problem, the first thing that we should start off with is working from the outside. Working from the outside, the fourth root, we can change that to a rational exponent or fractional exponent because the fourth root just represents the 1/4 power. Remember, this value will always represent the denominator of your exponent. And now we can do the same thing again. The cube root represents the 1/3 power. So we have x to the 1/3 power now being raised to the 1/4 power. And now remember our rules for exponents. When you raise an exponent to another exponent, you multiply the exponents together. So when you multiply two fractions, you multiply straight across, multiply the tops and the bottoms, which gives us x to the 1 times 1 is 1, over 3 times 4 is 12. And now converting it back to a radical, now that we've simplified, remember this 12 represents the radical index. So we get the 12th root of x. The fourth root of the cube root of x is the same thing as the 12th root of x. All right. So for this next one, this one is a bit trickier, but I would still like you to take a moment to try to pause the video. Go ahead and give this a try, see how far you can get through it. Okay, so now let's go ahead and try this together. The first thing we're going to do is notice that we have a fifth root, so we can change that to a 1/5 power instead of a 1/4 power like here. So we have x to the 15th, y to the 4th, z to the 10th, all to the 1/5 power. And with that, remember that whenever you have a bunch of values being multiplied together, all raised to an exponent, you can distribute the exponent to each term's exponent, multiplying them together. So that gives us x to the 15 times 1/5. I'll show this off to the side just for the first one. 15 times 1/5. We need to change this 15 to a fraction, so we'll put it over 1. You can put anything over 1 and it doesn't change the problem. And now that we have two fractions being multiplied, we will multiply straight across, which gives us 15 times 1 is 15, over 1 times 5 is 5, and 15 divided by 5 is 3. So x to the 15th to the 1/5 becomes x cubed. Y to the 4th to the 1/5 becomes y to the... Go ahead and try this off to the side for just a moment. Well, hopefully you already did, actually. And when you do that, it's going to be the same process. 4 times 1/5 will give us 4/5. And then again, 10 times 1/5 will give us 10/5, or z to the 2nd. And now from here, anything that still has a rational exponent that didn't simplify fully needs to go back inside of a radical. Everything that removed its fractional exponent is now outside of the radical. Just like when we worked in the last video, when you would pull factors out of the radical, because these no longer have fractions in their exponents, that is the same thing as saying they've been pulled outside of the radical. So I'm going to rewrite this first, just to make it look a little nicer, by rewriting the non-rational exponents in front. So x cubed and z squared are now in front, and y to the 4/5 is now in the back, because this is going to go back inside of the radical. So we get x cubed, z squared, and then y to the 4/5. This is going to change with a fifth root. So we have the fifth root of y to the numerator, y to the 4th. Remember, this was the first way that we talked about changing rational exponents to radicals. And in fact, I think I can bring it right here. This is what we did right here. When we couldn't simplify it, we said to just put the root with a to the numerator, the mth power. So that's exactly what we just did here. We could not simplify y to the 4/5. The fraction wasn't large enough, so we just put it back inside the radical, the fifth root of y to the 4th. And this is completely simplified. X cubed z squared times the fifth root of y to the 4th power. The last problem that we need to work on is 8 to the negative 2/3 times 8 to the 1/2 times 8 to the 1/6. Remembering that all of our fraction rules, or exponent rules that is to say, that we talked about in the last video still apply. Go ahead and take a moment. See if you can solve this problem. Okay, so now let's go ahead and try this together. Notice we are multiplying all three terms with the same base. We know that when you're multiplying with the same base, our exponent rules say that you can keep the base and just add all of the exponents together. So we get 8 to the negative 2/3 plus 1/2 plus 1/6. To combine these fractions, however, we are going to need a least common denominator. So I'm going to do this off to the side just to make it a little clearer, as I know that's a bit small. The least common denominator between 3, 2, and 6, meaning the smallest number that all three of these can divide into evenly, would be 6. 6 is divisible by 3, by 2, and 6, and it's the smallest number that's divisible by all three of them. So we need to change all of these denominators to 6's, so I'm going to multiply this 3 by a 2 to change it to a 6. And when I multiply it to the denominator, I have to multiply it to the numerator as well. The same thing is going to happen here. We are going to multiply the top and bottom by a 3 to change this 2 to a 6. And over here, this last fraction does not need to be multiplied by anything because we already have a 6 there. So we get 2 times negative 2 is negative 4, over 2 times 3 is 6, plus 1 times 3 is 3, over 2 times 3 is 6, plus 1/6. And now that we have a common denominator, we can add them together. Only when your bases are the same, when your denominators are the same, can you add the numerators. So we can add negative 4 plus 3 plus 1 all over this common denominator of 6. Negative 4 plus 3 plus 1. Well, negative 4 plus 3 is negative 1, plus 1 gives us 0 over 6, and 0 divided by 6 is just 0. So this entire thing, 8 to the negative 2/3 over 1/2 plus 1/6, becomes 8 to the 0 power, and anything to the 0 power except for 0 is just 1.